Hello, this is Theoretical Computer Science. We're doing section 1.1 of Sipser's book, Introduction to Theory of Computation. Okay, we're talking about finite automatons, and my name is Noson Yanofsky. Okay, so we're just going through what the section's all about. So what we said before was finite automatons are to be thought of as some type of baby computer that that can recognize a language. We're going to formally describe what it means to recognize a language, but I want to give you, we're going to start off with a lot of examples of finite automatons, and then we're going to go and talk about their languages, and then we'll give a more formal exact definition. So one of the things I said was a soda machine is an example of such a weak computer. Okay, and the soda machines understand the money input of $1.35. If you're lucky enough to live nowadays with a soda machine that just costs $1, where a soda just costs $1.35. To make things a little bit easier, we're going to have a soda machine that understands the language of just 35 cents. So we're talking 1950 or something like that. But that's okay, just to make it more simple. So let me just describe to you such a machine. Okay, we're going to draw a picture of it. Okay, I need all the room I can get. So you start off in a state, and the soda machine tells you what the state is. The state is 0 cents. Okay, when you come up to the soda machine, there's nothing in it. Now you can put a nickel in the soda machine, and then it's going to say 5 cents. And you can put another nickel in the soda machine, and then it's going to say 10 cents. And then you can put another nickel in the soda machine, and it can say 15 cents. And then you can put another nickel in the soda machine, and it says 20, 25, 30, 35. Okay, that's very good. And if you get to 35 cents, if you put in enough nickels, that's great. You get the soda machine. You get the soda. But there's something else you can do also. You can put in a dime. You could put in a dime at 5 cents and you get to 15 cents. You could put a dime at 10 cents and you get to 20 cents. You could put a dime over here. You could put a dime over here. You could put a dime over here. Okay. Now, there's something else that can happen also. You could put a dime over here, and then we're going to call the state return nickel. Okay? Because if you put a dime over here, you go from 30 cents to 40 cents. So, but a soda only needs 35 cents. And so you get the soda, but you return a nickel. Okay, great. Now, what else can happen? Well, I could start here, and I could put in a quarter. Or I can start here and put in a quarter. Or I can start here, 10 cents, put in a quarter, and get to 35 cents. Okay? Or I could start here, 15 cents, and put in a quarter. Okay? I'm going to do one more. Return dime. If you have 20 cents and you put in a quarter, you have 45 cents. You only need 35 cents to get to the soda, so it returns a dime. Okay, and you can actually go on like this. Okay, and now we can ask, what words does this language accept? So let's be a little bit formal. The alphabet is nickel, dime, quarter. Okay, and what you do is as follows. Let's go through some words that are accepted. Nickel, nickel, dime, nickel, dime is in the language. 5, 10, 20, 25, 35, it's in the language. Quarter, nickel, nickel is in the language. Let's just see why. Quarter, nickel, nickel is in the language. Quarter, dime, nickel is in the language. Let's see why. Quarter, dime, nickel is in the language. It's in an accepting state. These doubly circled things are called in accepting states. This single thing over here is a starting state. Okay, let's look at some things that are not in the thing. Okay, nickel, nickel, nickel. Nickel, nickel, dime is not in the language. Let's just see why. Nickel, nickel, dime is not in the language because it ends up in a non-accepting state. Okay, dime, dime, nickel is not in the does not last you in this you do not end up in the accepting. Dime, dime, nickel is there, so you're not there. Okay, so these are words. By the way, from just this you can understand something that's very interesting. Why is it that soda machines don't accept pennies? Okay, now the real reason is because pennies are made of a different metal and you'd have to check those different metals because of it. But here's another reason. Because if you had pennies and you wanted to get 35 cents, you'd have to have 35 different states. Okay, so your finite automaton would be much more complicated. In contrast, here, your finite automaton has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 states. 10 states is a lot less complicated than 35 cents. Okay, but if you added P for penny in here, then you'd have to have a state for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., etc. So that makes things a lot more complicated. So you don't want that. Okay, so that's our first example. And obviously this is a pretty simple example. We're going to do some more complicated examples. Okay, there's another example that usually I draw up in class, but it's just a pain in the neck. And actually, what I do is I give it out in a handout. Okay, and so it follows a story. And so let me tell you what the story is. The story is as follows: there's a man on an island, and he wants to go to another island. Okay, and he has with him three things. He has with him a wolf, a goat, and a cabbage. Okay, so there's a man on an island, and there's the man, there's a wolf, a goat, and a cabbage. Okay, and he wants to go to this other island, which at the moment has nothing. Okay, and he has one boat. Okay, he has one boat. Okay, the problem is as follows. He can't leave the wolf and the goat by themselves together, because then the wolf will eat the goat. He also can't leave the goat by itself with the cabbage, because then the goat would eat the cabbage. Okay, but wolves don't eat cabbage. That's the main point. Wolves don't eat cabbage. So how should he go here and take things with him? Okay, he doesn't have enough room in the boat to take all three at one time, and so he has to take one thing at a time. Okay, and the answer is he first takes the goat, because the wolf doesn't eat the cabbage, so he takes the goat and he brings the goat here. Okay, so the goat is no longer here, the goat is here. Okay, great. Then he comes back and he does one of two things. He either takes the wolf and brings the wolf here, but one second, if he brings the wolf here, he can't leave that here. So he takes the goat back. and he takes the cabbage. Okay. Now, there's a lot of different ways of doing this. It's okay, because in my handout to the class, and I'm going to show it to you here, this is formulated like this. It's formulated like a finite automaton. All the possible solutions are right here. You start here. Okay? You have the man, the wolf, the goat, and the cabbage in one place. You have the empty set in the other thing. And then you bring the cabbage. Then the man goes back by himself and either brings the wolf or the cabbage. Okay? And then he continues. Okay? At the end, he has nothing in the first island and everything in the second island. The main part about this is, how many possible solutions can you have? Well, watch what you can do. You can do this, 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 and there's two types of solutions. This, 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 this. You can go around here a couple of million times. Okay? And then you can go like this, and then and all you have to do is end up here. So there are a lot of different possible solutions here, and they're all outlined by this finite automaton. Again, you start with the man, wolf, goat, and cabbage on one side, nothing on the other side, and you end with nothing on the first island and everything on the second island. Okay? It's a cute little problem, but a little bit too long to write out. Great. Let's do another one. Okay. Okay. So the next one is very simple. We start off with simple examples. The alphabet is 0 and 1. Okay, and we're going to do that a lot. And the language is W such that, W is a word, such that W has an even number of zeros. Okay. Before we do it, let's go through some words that are in here and some words that are not in here. 0, 1, 1, 0, 0, 1, 0, 1, 0. Let's see. This has 1, 0, 2, 0, 3, 0, 4, 0, 5, 0. It is not in the language. It's not in that language. This is the language. The language is this, and it's not in that language because it doesn't satisfy. Okay? As opposed to that, 0, 0, 1, 1, 1, 1 is in the language. As opposed to that, not as opposed to that, in addition, the language 1, 1, 1 is in the language because it has 0 number of zeros. 0 is an even number. Okay? Here's another thing that's in the language. The empty word is in the language. It has 0 zeros and 0 ones. It's in the language. Okay? So it's good to see it. Okay, great. So what we do is we start off with a state. Okay? And by the very fact that the empty word is in the language, that means if I don't go anywhere from here, it's accepted. So the starting state is an accepting state. Whenever you have this phrase, the empty word is accepted, you automatically know that the starting thing is accepted. Okay, then we have as follows. If you have a 1, I don't care. Stay right there. I'm not interested in your 1s. Stay right there. Okay? If you have a 0, that means you have 1 0. 1 0 is not accepted. Now, once you're here, I don't care how many 1s you have. I have to tell you what to do at every state, what to do by every letter, but I don't care, so stay right there. Now, when you have another 0, you go back to the accepting state. And that's it. That's the whole thing. This thing is called a parity checker. You're checking its parity. You're checking odd and even. Okay, let's just go through these things. We're going to do this with this word. You ready? 0, 1, 1, 0, 0, 1, 0, 1, 0. He's here. He ends up here. He's not accepted. As opposed to that, let's do this. 0, 0, 1, 1, 1, 1, 1, 4 ones, he's here, he's accepted. 1, 1, 1, he's accepted. The empty word, he's accepted. Okay? So with one finger, you can follow the path along the finite automaton and determine whether or not it's accepted or not. Okay? That's very nice. Let's extend it. Let's extend this problem. So that's fine. Okay? We're doing another problem. W has an odd number of zeros and an odd number of ones. Here we have an odd number of zeros and an odd number of ones. Here we do care about the ones, so we have to be careful. First thing first, starting state. Oh, you know what? Let's do some words, see if what's accepted, what's not accepted. So 0, 0, 1, 0, 1, 0, 1. Let's see. This has an even number of zeros, not accepted. It has an odd number of ones. That's good, but it needs both of them. Okay? 1, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, 0. Let's do this. Let's do the zeros first. 1, 2, 3, 4, 5, odd. 1, 2, 3, 4, 5, 6, 7, odd. So this is a member of the language. Okay? By the way, the empty word is not in the language. Why not? Well, because it doesn't have it has a zero number of zeros, so it doesn't have that, it doesn't have, by the way, the number 1 is not in the language. The number 0 is not in the language. The number 0, 1, the word 0, 1 is in the language, because it has an odd number of zeros and an odd number of ones. Okay, so let's go through it. Here's the way it goes. What you're going to need is actually 2 parity checkers. Whereas before we didn't care how many ones we have, here we have to worry about how many ones. So here's what you do. This is even. I'm going to make this a little bit bigger because I can fill in this later. Okay? It's going to turn out that this is this thing. If you have a 0, you go here. If you have another 0, you go here. Okay? This is dealing with the zeros. Okay? Even amount of zeros, odd amount of zeros. But now we have to worry about the ones also. If you have a 1, I need to take that into account. I can't just stay where I was. And so I do this. And if I have another 1, I go back. Okay? Even amount of ones, odd amount of ones. Okay? Now, what happens if I'm here and I see a 0? I can't just go here. I have to go to another place, because I have to keep track of it. Okay? Even amount of zeros, odd amount of zeros. Okay? And if I have a 1 in here, then I have to do this again. Okay? Now, this state has 0 zeros and 0 ones, so that's even. And if you do this and this, you'll have even again, and do this and this, you'll have even again. So this is even zeros, okay? And also even ones, okay? And this state has odd zeros and even ones. And this state has even zeros and odd 1, and this state has even, odd zeros and odd 1. And this is our accepting state, because that's what we want, an odd number of zeros and an odd number of ones. Okay, and now we can again follow this. Let's just follow this. 0, 0, 1, 0, 1, 0, 1. It ends up here. Okay, let's do this one. You ready? 1, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, 0. Okay. The empty word is not accepted because you end up here. 1 is not accepted because you end up here. 0 is not accepted because you end up here. 0, 1 is accepted because you end up here. Okay, so that's a very nice little thing. Okay, let's do some more. It's a nice little example. Let's do some more. Okay. The alphabet is A, B. Okay, by the way, these are problems that are not done in the book. Okay. I never do problems that are done in the book. I do problem exercises from the book, okay, in the homework. So you see, when you're reading the book, you see my examples, you see the book's examples, and you see all the homework problems worked out. Either I'm going to work them out in class, or I do them in the homeworks after you do your homework. You do the homework and then you can check my answers. So you're going to see every problem of the sections that we do. So that's pretty good. Okay, so let's do this following language. The language is W such that W contains 2 B's. It could have more than 2 B's. Not dealing with that right now. And they need not be next to each other. Need not be next to each other. So I don't care about the string BB. I'm not looking for the string BB. They could be far apart from each other. Okay? So how do we do this? Okay. Now the first question is, what happens if it has 3 B's? Well, if it has 3 B's, then it has 2 B's. So we're happy with that. Okay? Okay, so here's the way you do it. You should stop the computer and try to do it on your own. Okay? Stop the video and try to do it on your own. Okay? You start in a state. You have nothing. If you have an A, I'm not interested. If you have a B, that's great. Then I go to a state which says I have 1 B. Now here, I don't care how many A's you have. It's not interesting to me, the A's. I just want to know how many B's you have. If you have another B, then great. You have 2 B's. That's accepted. Okay? Now, what happens if you're here? Well, I don't care if you have more than 2 B's or more than 2 A's, so you go here and you just write AB. That means stay here. Once you're accepted, once you have 2 B's, stay here. Okay? Great. Now, I could have drawn this down. I could have drawn it diagonally. I could have drawn it this way. I could have drawn it that way, going this way. It doesn't matter. These are all pictures, and pictures can be drawn many different ways. But I'd like to give you a really formal way of writing this thing. Okay? And the formal way is what's called a transition matrix. Now notice, I didn't really give names to these states beforehand Because I wasn't referring to them. I was pointing to the pictures, and you can see which state is which. This is the state that has no b's. This is the state that has one b. This is the state that has two b's. But right now I'm going to give them a name because I want to refer to them over here. Okay? And this is what's called the transition matrix. We're going to write it like this with a little delta over here. And what it says is, tell me what state you're in, tell me what letter you see, and I'll tell you what to do. So there's one of three states, Q1, Q2, Q3, and you either see the letter A or you see the letter B. Okay, and look what it says. It says if you're in Q1 and you see an A, you stay in Q1. If you're in Q1 and you see a B, you go to Q2. If you're in Q2 and you see an A, you stay in Q2. If you're in Q2 and you see a B, you go to Q3. If you're in Q3 and you see an A, you stay in Q3. And we wrote it again there, you stay in Q3. Okay? And sometimes we write this mark to show that that's the starting state. Okay? But that's it. Nice? So this picture is described perfectly by this matrix. Okay? Transition matrix. How do you transition while going from state to state? Great. Let's do another problem. Okay? You have to erase this and rewrite it. I don't have to erase this because I have this here. So I'm going to erase this because we don't need this. This makes total sense. Okay? And so we have this following. L, let's do another example. I'm doing another example. L, W, where W contains exactly two B's. Not one B, but not two, exactly two B's. Not one, not zero, not three, not four, not five. Now, again, you should stop the video and try to do it on your own. But what you'll see is as follows. Okay? When you do it, you'll get the following matrix. It says, or the following picture. It says, look, I want two B's. If I get an A, I can stay there because I can have all the A's I want. But if I get another B, I have to leave this state. And I go into another state because now I have more than two B's. This state was accepting. This is not going to be accepting. I'm going to call this state a garbage state because it's a state where you always stay there and you never move out. In other words, once you go into the garbage, you stay there forever and ever. Okay? When you get another B, I want you to go to the garbage state because if you have three B's, any word with three or more B's goes to the garbage. And that's that. Okay, so that's a nice example. Okay, great. Now, I'd like to give you a formal definition of what it means to be a finite automaton. We've already seen, I think, the soda machine, the goat, the wolf, and the thing. We've seen three more examples. 1, 2, 3, 4 more examples. So we've seen 6 examples. I'd like to be formal and give you a formal definition now of what a finite automaton is. Okay? And we're going to see this definition many times, variations of this definition many times in the coming pages. So you really have to get a feeling for this. You really have to understand this. So formal, that means exact, definition of a finite automata. Okay, just a little on the English. Finite automaton is singular. Finite automata, with an ending with an A, that's plural. So, give a finite automaton, or the set of a finite of this section is called finite automata. That's plural. Okay. Okay. A form of a finite automaton is a 5-tuple. Okay? Double, triple, 4-tuple, 5-tuple. It consists of 5 things. Okay? And I'm going to write the 5-tuple here. Q, sigma, delta, Q0, F. Okay? And I'm going to write it over here, what each one of these are. Okay? Q is a finite, hence the word finite automaton, set of states. A finite set of states. We draw the states with zeros, big circles. We make those are the states. Okay? And there's a finite number of states. Sigma, that's the next thing, is a finite set of symbols. Okay? What do we call a finite set of symbols? An alphabet. Okay? And the main point is, this is an alphabet. We're going to look at words in the alphabet, and we're going to follow the finite automaton with the words, and we're going to see, is this word accepted or is this word not accepted by the finite automaton? Is this word accepted or is this word not accepted by the finite automaton? Okay, great. Delta, we'll deal with that in a second. Okay? Delta is a transition function. Transition function. How does it transist? We'll deal with that in a second. I want to do the easier parts first. Delta is the core, the heart of the machine. It's the program of the machine. This is telling you what the states are. This is telling you what the possible inputs are. This is the real program. Okay? Let me tell you what Q0 is. We'll come back to 3, so leave me room for 3. Q0, member of Q, it's one of the states, okay, is a starting state. It's where you start reading the words. Where you start reading the words. Okay? And finally, F. This is a single starting state. F is a bunch of states. Okay? And they're called accepting states. Okay? F is accepting states. It's a bunch of states. And how did we draw accepting states? We drew them. This is a state, an accepting state. We drew 2 circles around them. Okay, great. Now, what the hell is the transition function? The transition function is exactly the transition matrix. It tells you how to go from one state to the next state. How do you go from one state to the next state? Okay? And it goes as follows. Delta is a transition function. Okay? Now, we drew it with little circles for the states, and we have little letters telling you how to go. But I want to be a little bit formal about it. I don't want to just draw pictures, so I want to write it as a function. And basically what it says is, you give me a state, and give me a letter. Give me a state and a letter, and I'll tell you what state to go into. Okay? Now we draw this as a transition function as follows, and that's why I drew this delta here. You tell me what state you're in, you tell me what letter is, and I'll tell you what states to go into. That's the inside, that's the output of this function. Okay? Well, let's write it up like this. We say as follows. Delta, you're in state Q37. You see the letter J. Let's not use J because J looks like a semicolon. You see the letter T. Okay? Then you should go into state Q52. That's the typical type of output you'll have for this type of function. Okay? This is an exact definition of what I mean by a finite automaton. We did 6 examples. It's an idea to go back to those 6 examples and see what the states are, what the alphabet is, what the transition function is, what the starting state is, and what the accepting states are. We did it while we were doing it. We showed you what these things were while we were doing it, but that's easy. Also, the homework starts off with easy homeworks to make sure you understand these concepts very well. But we're not interested in this. I mean, obviously we're interested in, you are responsible for this, and you will be asked to do formal definitions in tests, but we want to get back to more examples, because the examples are where the fun is. Okay? Okay, great. Okay. Let's do some more examples. The alphabet is A, comma, B, and the language is equal to those words such that W does not contain 2 B's. Okay? We saw something very similar to this 2 minutes ago, but here we say, before we said W does contain 2 B's, now we say does not contain 2 B's. Okay? Well, let me teach you a trick about doing the word not. Whenever you see the word not, here's what you do. Cover it over, okay, and write the finite automaton that does this. W does contain 2 B's. Well, we just did that 5 minutes ago. So let's just do it again. B, A, B, okay, A, comma, B, and this was an accepting state. Okay, but now we want does not contain 2 B's. And so what we do is we say as follows. Look, anything that did contain 2 B's, we don't want that accepted. So we want those things that do not contain 2 B's. So anything. So this will no longer be an accepting state. In contrast, this will be an accepting state. This will be an accepting state. Okay? So what we did was we swap. To do the not, we swap accepting states for non-accepting states. Change. The accepting states become non-accepting states. The non-accepting states become accepting states. Okay? And then you're going to get not. Okay? Because anything that landed in the non-accepting states does not have the requirement. So that's very good. Okay, great. Let's erase. Okay. Okay. I'm doing now problems from exercise 1.6. We do the harder ones, and you're left to the homework to do the easier ones. So this is 1.6F, I think. I'm sorry. This is 1.6F. Okay. So let's do it. The alphabet is 0, 1, and it's those words, the language is those words such that W does not contain the substring 110. Now, this is different than what we had before. Before, when we were talking about 2 B's, we didn't care if they were next to each other. Now, we care that it's a substring 110. Okay? It has to be that form. Okay, now, how do you deal with the word not? Answer. Cover over the not and solve the problem like this, and then we'll swap. So let's cover over the not, okay, and solve the problem. So look what you want. You want to start someplace, and then you want to see a 1, and then you want to see a 1, and then you want to see a 0. And that's going to be accepting. I'm going to erase this later on because I'm going to swap the accepting states and the non-accepting states, but for the moment, let's write it. Okay, great. Now, what happens if you're here and you see a 0? Well, you stay right there because you're waiting for a 1, 1, 0. Okay. What happens if you're here and you see a 1 or a 0? Well, I told you I'm looking for something that does contain the substring 1, 1, 0. I don't care what happens afterwards, so I stay here. Okay, great. Now again, for this finite automaton, I have to tell you at every state what to do for every letter. So if there's a 0 here, I go here. If there's a 1 here, I go here. Now, if there's a 1 here, I go here. But what do I do if there's a 0 here? Okay, now this is very interesting. I don't stay here if there's a 0 because I want the phrase 1, 1, 0. Okay, I want it to get here, I have to see 1, 1, 0. So if I see a 0, if I'm here and I see a 0, I have to go back again and wait till I see a 1, 1, 0. Good. Now I'm here. I just saw a 1 and a 1. I'm here. Okay? Now, if I see a 0, that's great. I go here. Then I'm in. I'm done. But if I see a 1, where should I go? Now, in contrast to going backwards, if I see a 1, look where I should go. I should stay right there. Why? How come over here I went back and over here I didn't? Okay? And the answer is because when I'm here, and I see, I just saw 2 1s, 1, 1, and I see another 1, I wait here because I just saw 3 1s, so 1, 1. That's good. And I see another 1, I stay here because that might be the other one. If I see a 0, I'm done. Okay? But I could see 50,000 1s and stay right here. Okay? This is very important. Okay? Now, I'd like to show you some words to fit in to see if it fits in. So let's do it. 1, 0, 1. Yeah, that's too easy. 0, 1, 0, 1, 1. 0, 0, 1, 1. Let's do this. You ready? Start here. 0, 1, 0, 1, 0, 1, 0. This is really uninteresting. 1, 1. I'm here. Not accepted. I'm here. Okay, this does not contain 1, 1, 0. Okay? That still lands in here. Okay, great. So that works. This is not in, oh, well, it's not in the language, but great. Now, but you have to understand why over here we go back and over here we wait. Okay, and we'll see a lot of these in a second. Great. Now, I'm finished covering over the not. Let's take out the not. So I swap. This is no longer an accepting state. And this is an accepting state, and this is an accepting state, and this is an accepting state. By the way, notice the empty word does not contain the string 1, 1, 0. Therefore, the empty word is an accepting state. I'm sorry, the starting state is an accepting state. Okay, great. Some more. This is 1.6G. The alphabet's the same. Okay, let's see what it says. The length of W is at most 5. The length of W is at most 5. Okay. This is actually very simple, and I'm going to do it very quickly, but you should try to do it on your own. Let me just do some English here. At most 5 means it's 0, 1, 2, 3, 4, 5. Okay? It can't be 6. That's what at most 5 means. So, at most 5 could be there. By the way, another way of writing this is the length of W is less than or equal to 5. Okay? The empty word is accepted, but you could have another state in the empty word, and that word would be accepted. You could have another letter, and that would be accepted. You could have another letter, and that would be accepted. 1, 2, 3, and that would be accepted. 1, 2, 3, 4, and that would be accepted. Okay, but if you have anything more, you go to a garbage state and you stay there. Okay. Now, in every single example, and so far you've seen, I think, 8 examples, I've always done the same stupid thing. I've been giving you a language and asking you to find me a program, a finite automaton, that recognizes those words in the language. Okay? But I want to say, I can go the other way also. I can give you a finite automaton and ask you, what words are accepted here? So if I close this up and I gave you this machine, you'd be able to figure, look, it's accepting words of length 1, 2, 3, 4, etc., etc. So that's pretty nice. Okay. Okay, let's do a silly problem. Okay, 1.6h, which is as follows. The language is equal to words such that W is any string except, what's that word mean? 1, 1 or 1, 1, 1. Okay? Any string except those 2 words. So this language takes a long time. Okay, but we're going to do it. Any string except 1, 1. So a lot of words are accepted in this language. These are the only 2 words that are not. Except is another way of saying not. So we're going to cover it up. Okay, so I want words that accept 1, 1 or 1, 1, 1. So it's very simple. By the way, you should try to do it on your own. Stop the machine and try to do it on your own. Okay? If you accept 1, 1, then you're accepting. If you accept 1, 1, 1, then you're accepting. If at any point you see a 0, you go to the garbage. Okay? Even here, go to the garbage. Now, what happens if you see a 1 over here? I'm only accepting this or this. Well, if I see another 1, I go to the garbage too. That's it. Great. Now that's any string 1, 1 or 1, 1, 1. That's fine. Okay. But now I want everything except those. So what I have to do is I have to erase those 2. Those are no longer accepting states. Okay, you have to rewrite this because you don't have a whiteboard, but I don't. Oh, by the way, this is a garbage state. But now look what happens. Because I use the word accept, I have to swap the accepting states for the non-accepting states, and so these become accepting states. Look at this. The garbage state becomes an accepting state. Okay, and in fact, most of the words end up here. Okay, That's very nice. Okay, two more examples. Two more examples. Okay, 1.6i. I told you we'd do all the problems in this book. It's a very good book. Okay, and it goes, every odd position is a 1. Every odd position is a 1. Okay, let's go through some words to see what's in it and what's not in it. Okay, so one is an accepting is in the language because there's one thing and it's a 1. Okay, 1, 0 is in the language. The empty word is in the language. Why? Because what's in the odd position? There's nothing in the odd position. There is no odd position in this word, so it's accepting. Okay, 1, 0, 1 is in the language. 1, 1, 1 is in the language. That's the first position. That's the third position. It's in it. Okay, 1, 1, 0 is not in the language because that's in the third position. There's a 0 there. It's not good. Okay, 0, 1, 1 is not in the language because that's the first position and there's a 0 there. Okay, 1, 0, 1, 1, 1, that's in the language. First position, third position, 5 positions, they all have a 1. Notice I don't care what happens in the even positions. Okay, so let's do this. You ready? First of all, you have a starting state. You always start with a starting state. But, second of all, the starting state is accepting. Now, what I want, maybe I'm wrong, hold on. What I want is, I don't care if I have a 1, then I go to this state. And it's still accepting, because look, 1 is accepting. That's very good. But I need a little parity checker. I have to go to the other state because I have to say this is an odd position. Now, here, if I get a 0 or a 1, I go back to the original thing because I don't care what happens at the even positions. I don't care what happens at the even positions. Okay, it could be a 0 or a 1. The only thing I do care is as follows. If I'm here waiting to have another letter, I'm here, that means I'm waiting to do the odd position. If I have a 1, it's good. If I don't have a 1, if I have a 0, then I want to go to the garbage state and stay there. That's it. Okay, and we can go through all of these. 1 lands here. 1, 0 lands here. The empty state lands here. 1, 0, 1 lands here. 1, 1, 1 lands here. 1, 0, 0 lands in the garbage state. 0, 1, 1 lands in the garbage state. 1, 0, 1, 1, 1. It's good. That lands in the language. Okay? It's a nice problem. Again, we have this little parity checker because we want to count what's an odd position, what's an even position. Okay. Great. Last problem, 1.6J. Okay. W contains at least 2 zeros and at most 1 1. Okay. Again, I strongly urge you to stop the machine and try to do this on your own. Okay, it's a hard one. It's the last one in the exercise, so it's a hard one, but it's doable. Okay, and what you have to do is go through first. What does it mean? Contains at least 2 zeros. That means it contains 2 zeros or 3 zeros or 4 zeros or 5 zeros. What does it mean it contains at most 1 1? Oh, it contains 0 ones or it contains 1 1. Okay, and you do it. So stop the machine and try to do it. Try to write some words that are in the language and not in the language. Okay, and you'll get a feel for it, and it's a lot better than just watching me do it. Okay, stop the machine and now start the machine again, see if I got it right. Okay, that's it. Basically, this way is having zeros, and so you can't have 1 0, you can't have 2 zeros. So you can have 2 or more zeros, and when you have more, you go like this. And then every time you have a 1, well, you could have 1 1. You can have 0 ones, that's up here, or you can have 1 1. I don't care when you have the 1. And then if you have any more ones, you go to the garbage and stay there. Okay, great. So I think we saw like 10 different examples of finite automatons. We're going to do a lot more in the next section, but now we have to go back and do a little bit more theory, okay? And it'll take a few minutes, and that's that. So again, this is in the book, and really you have to read the book on your own, but I'm just helping you do the book. Okay, so what we want is as follows: a formal definition of what it means for a word to be accepted by a machine. And I'm doing this because it's simple, because we already know what it means, okay? But also, as the book goes on, it progresses with this definition and advances with the more advanced machines that we're going to see. As I told you before, we're down here, we're talking about finite automatons, okay? But we're going to see a lot more complicated machines as we go on, and so we need to know what it means to be accepted. Now, this is the central point of formal language theory. The central point of formal language theory is that for every machine there is a language. For every language there is a machine. Okay? And so we want to know what it really means. Now, we understand what it means because we've been doing that since the beginning. Since the first example, I've been putting out words and we're seeing, is the word accepted, is the word not accepted? And we're bouncing back and forth and following it along. Basically, I've been doing it with my finger. Okay, we start at the starting state, we bounce along, bounce, 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 and then we see, are we accepting? Okay, but I'd like to be formal about it, because this is what it is. It's all about learning how to read this book. So, let's be exact. Let M equal, M is a machine, it equals to the 5 tuple, set of states, the set of the alphabet, the transition function, Q0 and F. Be a finite automaton, FA, finite automaton. And W, that's a word, we're going to write the word with its letters, W1, W2, W3, dot, 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 Wn. Those are the letters of the finite, of the word. Be a string in sigma. Okay? Period. Then M accepts W. That's what we're describing. What does it mean for the machine to accept the word? If there exists a sequence of states, we'll call the sequence R0, that's the first state, R1, that's the second state, R2, that's the third state, dot dot dot, Rn, that's the nth state, sequence of states, such that, okay, and we're going to have three requirements. 1, 2, 3. And you can already say what the requirements are even before we look at it, but let's do it together. First requirement is, where did my finger always start? By the way, my finger was making this sequence of states the whole time. I was going like this, bouncy, 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 bouncy. Always okay? Every state I was pointing to would be one of these. Okay, so first, where does my state start? Answer, R0 equals Q0. What's Q0? It's the starting state. So my finger always started pointing at the starting state. Finally, when I was finished with my states, where was I? Rn, what does it mean to accept the word? Rn is a member of F. It's accepting, okay? It's in an accepting state. If the final thing, if my finger stops bouncing at an accepting state, then the word's accepted. Okay, great. Now for the hard part. How did my finger move around? How did my finger move around? Answer, it was following the transition function. It was following this delta. It was doing exactly what the arrows told me to do. And so we write this as follows. Delta of Ri, comma, Wi equals, Ri plus 1 for I equals, I start at 0? Yeah. 0, 1, 2, n minus 1. In other words, you went from state to state by looking at each word and going along. Okay? Looking at each letter, you're in this state, you look at that letter, and you go to the next state. So this sequence that I was doing with my finger is exactly this. Okay, great. That's what it means for a finite automaton to accept a word. And we're going to see later how we're going to change this over and over and over. Okay? So again, what we did here was we took a simple intuition which we had from the first example. Okay, we took a simple intuition and we formalized it in being exact. What does it mean for a word to be accepted? You start at the starting state, you transition the way the transition function tells you to, and then you end in an accepting state, then the word is accepted. Great. Now, let's do the next. Machine definition. Machine M recognizes language L if L, so this is a definition, we're defining the word recognizes. And I told you this is what formal language theory is all about, that machines recognize certain languages. Okay? And the more complicated the machine is, the more complicated the language is. So now is the core of this thing. Machine M recognizes language L if the language is equal to those words such that M accepts W. Okay? So we say as follows. If the machine accepts those words in the language, exactly those words, no other words, okay, then the machine recognizes the language. Okay, great. One more definition. A language is regular. That's what we're defining. This is the first real definition we had. Regular languages. Okay? And I'm down here. We've spent the first class talking about finite automatons, and now I'm describing the language type that corresponds to that, and that's going to be regular languages. So a language is regular if some finite automaton recognizes it. So these baby machines called finite automatons, all the languages that are recognized by these baby machines, they are going to be called regular. And we're going to see as we go on, there's many other languages that are not recognized by finite automatons. They need more sophisticated languages to recognize it. Okay? Okay, great. I just want to draw a picture before we close up shop of what we did today. Okay? And it's a picture that I'm going to draw every single class. Okay? And we're going to add to this picture over and over and over, but it's a picture you have to see, and again, you should keep it and you realize what it is. Ready? Let's start with what we did the first day of class. Alphabet. Words. Subsets of words. We have a word for subsets of words. We call them languages. Okay, and so this is the set of all languages. And now we said as follows. There's a special types of languages which we call regular languages. Each dot over here corresponds to a subset of languages. A subset of words. Each dot corresponds to a subset of words, and we call these regular languages. Okay? Now what we saw over here, and I told you this beforehand, languages correspond to machines. That's the central point of formal language theory, and so these are going to correspond to finite automatons. So finite automatons are going to correspond to regular languages. We're going to build this picture up. We're going to have other languages. We're going to have other machines. And this is going to be very pretty. But so we're going to have two different, the first half of this class is all about finite automatons, formal language theory, and we said formal language theory has to do with this correspondence between machines and language. And so this is what it is. Okay. We are now finished section 1.1, and we'll do section 1.2 tomorrow. Okay, have a nice night.